This is Lesson 15, Solving Quadratic Equations. In Lesson 14, we looked at the graphs of quadratic equation, parabolas. And now we're going to solve equations in one variable that contain a square term. Thus, there are quadratic equations. It's going to actually take us about 2 lessons to cover the material. In this lesson, we're going to look at 3 particular methods of solving quadratic equations. And then we're going to begin to go towards a universal method of solving all quadratic equations. But as I've mentioned before, all of these are generally discussed in your textbook, and you may have a teacher who wants you to be able to solve quadratic equations in more than one way. The first method, of course, of solving quadratic equations is by solving an equation of the form ax squared plus c. You can go ahead and write that on the board over here. And I think I said ax squared plus c. I meant ax squared equals c. How do we solve that? Well, that is simply a quadratic equation. We want to isolate the x squared and take the square root of both sides. So we divide both sides by a and then take the square root of both sides. For example, if we get an answer or a situation we have x squared equals 25, when we take the square root of both sides, we're going to get 2 answers. We're going to get x is equal to 5 as well as negative 5, since negative 5 times negative 5 is 25. The way we write that is plus or minus the square root of 25, which is plus or minus 5. That is, positive 5 and negative 5 would both be answers to this particular kind of problem. Let's look at a very specific problem. Let's look at the first visual in this lesson, which is 3x squared equals 48. 3x squared equals 48 is ax squared equals c. That's the type. What's the first thing we do? Well, on the second line, which is shadowed in for you, we have x squared equals 16. How do we get that? We divided both sides of the equation by 3. And then we take the square root of both sides of the equation, and we get our solution. X equals plus or minus 4. What should we do next? We should check. And we go back and check plus 4. 4 squared is 16 times 3 is 48. We can check negative 4. Negative 4 squared times 3. 3 times 16 is 48. So in this case, plus 4 and minus 4 are both answers to the original equation. And in fact, in most quadratics, we'll have no more than 2 answers. It's a good way to remember. Linear equations, when we had 1 answer, we had those absolute values. That was a little something different. And in the quadratics, we have a maximum of 2. There'll be times we appear to only have 1 answer, and sometimes we'll see we might get an equation where there's no answer. Let's look at the next equation. We have x squared minus 2x minus 35 equals 0. That is not of the form ax squared equals c, is it? In fact, it's of the form ax squared plus bx plus c equals 0. This is a very important form of equation because we'll see later on it will help us better graph those parabolas we were dealing with in the previous lesson. Notice what we did here. We went back to a previous lesson where we learned about factoring, and we factored x squared minus 2x minus 35. And of course, we may recognize this is a quadratic trinomial, and we need 2 numbers that multiply to be 35, whose difference is 2. 7 times 5 seems to work. The larger number, 7, has to be the negative, so we get x minus 7 times x plus 5 equals 0. And that's on line 2. On the next line, we actually solve. Now, how do we solve? Well, it's very simple. If I tell you I have 2 numbers that I've multiplied, I have 1 number in one pocket and 1 number in the other pocket. When I multiply those 2 numbers, the answer I get is 0. What do you know about at least one of those numbers? What you should know is at least one of those numbers must be 0. Because I cannot multiply 2 non-zero numbers and get 0 in our number system. Which means that one of the 2 factors, either x minus 7 or x plus 5, must equal 0. So I set each of those factors equal to 0, and that's what's seen on line 3. and I solve. Well, obviously, if x minus 7 equals 0, I get x equals 7. If x plus 5 equals 0, I get x equals negative 5. Thus, I have my two answers, x equals 7 and x equals negative 5. So, first we looked at a very simplistic quadratic equation. We have something x squared equals a number, and then we've jumped into where we have both the quadratic term, the ax squared term, we have the linear term, the bx term, and the constant term, the c term. Now, let's take a look at another example here. This one may be a little more difficult, a little more challenging. Let's erase this easy one over here. It's of the same type where we're going to wind up factoring, and it's the factoring that may take a little more effort. So, for example, here is this equation, 6x squared minus 5x minus 4 equals 0. Now look at that equation and tell yourself, because you can't tell me obviously, what makes that different than the previous one we had. It's a quadratic trinomial. There appears to be no real problem except for one thing. In the previous problem, the coefficient of x squared, the a term, was 1. Now it's not 1. And remember we talked about this in factoring quadratic trinomials. When a was not 1, we actually had to play a little trial and error game here. And I've already done that for you. Oops, wrong problem. Let's see, we need two numbers in our x that multiply to be 6 and 2 and 3 work. I need two numbers that multiply to be 4. It could be 2 and 2 or 4 and 1. And my answer says the answer is 1 and 4. And now I've got to watch my signs. I know the signs are going to be opposite because I have a negative 4 as my constant term. So let's see. It turns out after some experimentation that this will work. But let's double check it. Just because it's on my sheet of paper doesn't necessarily mean it's correct. 2x times 3x will give me the 6x squared. And I know the 1 times the negative 4 will give me the negative 4. This will give me positive 3x. This will give me negative 8x. A positive 3x and a negative 8x gives me negative 5x. This is the proper factoring. Now, once we've got it in this form, we set each factor equal to 0. 2x plus 1 equals 0, and 3x minus 4 equals 0. As we'll see, the answers this time will not be as clean or as simple as the ones for the previous problem. We subtract 1 from both sides and divide by 2, and we get x equals negative a half. The other solution, we add 4 to both sides and divide by 3, and we get x equals 4/3. Once again, we have two answers, and those two answers are both fractions. If you wanted to take the time, which I will not do here, but I recommend that you do it to ensure that you can work with fractions in algebraic equations, is take the negative a half, replace x with negative a half, and see that this whole thing is equal to 0. Then go back to this original equation and replace x with 4/3 here, and this left side should be equal to 0. It will be because these are the correct answers. It should check. Now, let's look at a little bit different wrinkle in a problem. That's to be seen in the next visual. What's different about this? Well, we have an x squared. We have a number term. Well, in fact, we have two number terms. And in fact, we don't have is equals 0. We have, at the very first line, we have an equation that has x squared plus 8 on the left side of equals and 7x plus 16 on the right side of equals. What do? Well, what we've done so far is we factored when we had ax squared plus bx plus c equals 0. So we've got to make this look just the same way. And as it's highlighted on line 2, we've subtracted the 7x from both sides, we've subtracted the 16 from both sides, and got x squared minus 7x minus 8 equals 0. Now it's in the proper form. So all you've got to do is, if you get a quadratic equation to solve that looks messy, is get everything on one side equal to 0. Okay, back to that visual, because now we factored, and obviously we need two numbers to multiply to be 8. Opposite signs, we subtract, we get 7. 8 and 1 seems to work, so we get x minus 8 and x plus 1 equals 0. We set each factor equal to 0 and solve, and we get x equals 8 and x equals negative 1. So, what we've seen so far is we can set a quadratic equation equal to 0, and we can factor. And of course, all the problems so far, we've been able to factor. But what if you couldn't factor? What if it was something that you didn't know how to factor? You tried every possible scheme and it did not work. Are there polynomials like that, quadratic polynomials? Yes, of course there are. And therefore, we've got to come to a better way. Now, what we're doing now, and for just about the rest of this lesson, is we're looking to come up with a universal method of solving any single quadratic equation. And in fact, we're going to do that, actually use that universal method in the next lesson, Lesson 16. But right now, we want to develop that. And again, we come to one of those points in this tape series where I'm going to do something that you might be a little confused about. We're going to develop a method, and you say, gee, that is really tough. That's a tough way to do that. And once you see where we're going, and in the next lesson you see the use of the quadratic formula, this universal method, you say, why did you do that in the first place? Well, again, my feeling, my philosophy is I want my students to understand where things began, how we got to where we are now. And what we're going to do next, which is called completing the square, is how we get to that universal quadratic formula. So, let's go ahead and do it. Let's take a look at the next visual. And in this visual, what we've seen, if you've taken a binomial, actually we've taken 3 different binomials, x plus 2, and x minus 3, and x plus 3 halves. And we've squared those binomials. Multiplied it by itself and came out with this quadratic in the form ax squared plus bx plus c. What do we notice about this particular type of quadratic? What do we notice about it? Well, let's see. The first one we noticed that the 4, we got a 4 at the end. How do we get that? We squared the 2. Okay, 2 times 2. And how do we get that 4 in the middle? Well, we had x plus 2 times x plus 2. We had a 2x and we had another 2x, so we added them up. Well, if you add up 2x and 2x, that's the same as multiplying 2x by 2. So in reality, what we had is x squared plus 2 times the 2x plus 4, which is 2 squared. The pattern holds true in the next situation. X minus 3 squared. Notice the number in the middle, negative 6, the coefficient of x, is twice negative 3. And the 9 is the square of negative 3. And look at the third one, the third line. Exactly the same thing. We have x plus 3 halves squared. We double the 3 halves, we get plus 3. That's the number in front of the x. We square 3 halves, and we get 9/4. That's the number at the end. So all we've got to do is when we square a binomial of the form of x plus some number, is it's x squared, followed by twice that number, x, and then the number squared. And those are 3 good examples. Let's see how we use that knowledge to what's called complete the square to solve a quadratic equation. Let me go ahead and go to the board and write this equation on the board, and then we'll see how we use it. Now, we have x squared plus 4x plus 1 equals 0. Make that 0 look like a 0. Now, that is a quadratic equation. It is certainly a quadratic equation that is of the form ax squared plus bx plus c equals 0. We already have it set equal to 0. The question is, could you factor that? In order to factor this, you would need 2 numbers that multiply to be 1 and add to be 4. The only numbers I know that multiply to be 1 are 1 times 1, and 1 plus 1 wouldn't give us 4. So what are we going to do? We are going to attempt to make the left side of this equation into a perfect square. Using our knowledge of what a perfect square looks like when we square x plus some number or x minus some number. So let's look at the next visual. The next visual shows us that we've taken the 1 and subtracted it from both sides. x squared plus 4x plus blank equals -1. The reason for the blank is because we're going to fill a number in there that'll make that left side a perfect square. Well, how do we find what that number is? Well, look at the number in the middle. The middle term, the x term, is plus 4x. Okay? Remember, we got that term by doubling the number that's x plus that number squared. What number is doubled to get a positive 4? Well, I hope you understand and realize it's positive 2. So what we really have is x plus 2 squared is going to have that 4x in the middle. And notice in the line below we have x plus blank squared. We want that left side to be x plus blank squared, and the only number that will fit in there is 2. Why? Because when we square x plus 2, the middle term is 4x. Okay, but what is that missing term on that first line? What is that number term going to be? Well, x squared plus 4x plus, well, we know it's x plus 2 squared, and the 2 times 2 is 4. We're going to have to add a 4 in that blank on that first line. And if we add a 4 on the left side of the equation, what else must we do? We must do the same thing to the other side, and therefore we must add a 4 to the right side. And the next visual demonstrates that for us. What we've done is we've added a 4, which you'll notice is in blue, to both sides, the left and the right, taking the equation x squared plus 4x equals -1, and making it x squared plus 4x plus 4 equals 3. Now, since the left side of that is a perfect square, we write it on the second line, which is highlighted. We write it as x plus 2 quantity. That means in parentheses, x plus 2 quantity squared equals 3. And now we're kind of back to where we were at the very beginning. We have something squared equals to a number. What do? We take the square root of both sides. The square root of x plus 2 squared is x plus 2. Why? Because the square root of a square means you do something and you reverse it, and you're back to where you started from. So if I take the square root of x plus 2 squared, I get x plus 2. The square root of 3, I don't know what that is exactly. It's some number. It's some number between 1 and 2, and we're not going to worry about it. But the fact is, I get 2 answers because it's plus the square root of 3 or minus the square root of 3. Thus, on the third line of the visual, we see that it says x plus 2 equals plus or minus the square root of 3. Okay. That's our answer. No, it's not. We don't want to know what x plus 2 is. We want to know what x is. So what do now? We isolate the x. We subtract 2 from both sides. And instead of putting plus or minus 3, square root of 3 minus 2, we put the -2 in front. It's the same thing, and we get -2 plus or minus the square root of 3. And now we also can see why we couldn't factor, because we couldn't factor because the answers, the numbers, are irrational. We have a square root involved. But -2 plus the square root of 3 and -2 minus the square root of 3 are the 2 answers to that original quadratic equation, x squared plus 4x plus 1 equals 0. You may be saying, that was a heck of a lot of work to do to get those 2 silly answers. And I agree with you. I agree with you because when we get to the quadratic formula, it'll take a couple of simple arithmetic steps and you'll have the same answer without going through all this rigmarole. Then why go through it? Because as I've explained, I want you to see where this comes from. So we'll probably do, let's say, couple of more problems. I know you may not like that. A couple of more problems of this type, which will lead us to a generalization, which will lead to this universal quadratic formula. I know that sounds very exciting, but I'm the boss. This is my tape, so we'll do it my way. All right, let's take a look at another example. Another example. And this time, let's do the whole problem at the board, so I can answer or ask questions. Let's see. The original problem is x squared minus 5x minus 7 equals 0. And again, I cannot factor this. The only numbers that multiply to be 7 are 1 and 7, and the difference in 1 and 7 is not 5, it's 6. This cannot be factored. I say that because if I could factor this, there's no need to use this method at all. Factoring is usually quite simple. All right, so what I'm going to do. The first thing I did was to get whatever the number was out of there. X squared minus 5x, and I add 7 to both sides to get rid of the negative 7. So what I now have is 2 of the 3 terms in what I want to be a perfect square. Now, the question is, I know there's an x in here because I need to get x squared. What is the sign in here? Well, we've seen that the sign in here is the same as the sign in this x term, which is negative. And I know that the number here, when I double it, I'll get 5. What number doubled is 5? Or a better way of asking that is, what is half of 5? And of course, half of 5 is 2.5, or 5 halves. So when I write this as a perfect square, I'm going to need to add the term that is the final term in x minus 5 halves squared. Because x minus 5 halves squared is going to be x squared, this is going to be minus 5x, and then, of course, plus this number. Why plus? Because even though this is negative, when I square it, I get a plus. And what is 5 halves squared? Well, a fraction, to square a fraction, you multiply the top and the bottom by itself. So I get 25 fourths. Well, if I've added 25 fourths to the left side, what else do I have to do? Well, I've got to add 25 fourths to the right side. Why? It's an equation. I've got to maintain the integrity of the equation. Uh-oh, everybody's favorite thing here. We've got to add 7 plus 25 fourths. Now, how are we going to do that? Well, remember, we need a common denominator, and 7 is 28 fourths. And again, these problems get pretty messy, but you'll see the same messy problems when we get to that quadratic formula will seem almost simple, and they will be simple. And now I add 28 fourths and 25 fourths, and I get 53 fourths. Let me erase this and put in 53 fourths. Well, now I have this perfect square equal to a number. I square root both sides. The square root of a square is what's inside. So x minus 5 halves. The square root of 53 fourths. When I take the square root of a fraction, I take the square root of the top over the square root of the bottom. The square root of 53, that's plus or minus the square root of 53. The square root of 4 is 2. And now I add 5 halves to both sides because I want to solve for x. And notice we have a common denominator, 2. So I'm going to simply write that as 5 plus or minus the square root of 53 all over 2. Now that's a typical looking answer for your quadratic problems. And again, this is something, what is the square root of 53? Well, it's about 7, a little more than 7. So we can figure out what this is approximately, which might be helpful. But the key thing is, unfortunately, in many of the quadratic problems we wind up solving, we get answers that look kind of like that. And the problem is not the answer. The problem is the steps we had to go through to get there. And I guarantee you, unless you have a teacher who loves completing the square, you might not have problems like this on a quiz or a test. But it is important to understand this so we can go on to the way we found this quadratic formula, because it'd be very simple to come down and say, here's the quadratic formula, use it. That's not my style. Okay, let's try one more problem. And this problem, let's go ahead and do that at the board too. I think it's just easier to do these at the board. Erase this here. This problem is going to have a little extra added attraction to it because it has a number other than 1 in front of the x squared. 4x squared plus 8x minus 3 equals 0. Okay? Now, we saw the perfect squares we had were the form x squared plus. We've got to get rid of the 4. Well, before we do that, let's get rid of this 3. Doesn't make a difference, but I just like to get the number out of there. So we'll have 4x squared plus 8x equals 3. We add 3 to both sides. Now let's get through the 4. Let's divide everything by 4. Easy enough to do. Fortunately for us, this is a number divisible by 4. Unfortunately for us, this is not. And we're back to dealing with fractions, which unfortunately is part of life in algebra class. Now what do we do? Well, we're back to having something we'd like to be a perfect square. What do we have to add here? Well, again, remember, let's jump to the next line to kind of help us, and that is this is going to be x and, of course, plus something squared. Whatever this number is, when I double it, I get 2. Or that is, what's half of 2? Half of 2 is 1. So this number has got to be 1. Well, if this number is 1, then the number over here in the perfect square is going to be 1 squared. If I add 1 to x squared plus 2x, I've got to add 1 to 3/4. And 3/4 plus 4/4 is 7/4. Now I take the square root of both sides. X plus 1 equals the square root of 7, so it's plus or minus the square root of 7, over the square root of 4, which is 2. I'm not done yet because I want my answer in terms of x equals. I need to get rid of the positive 1. I subtract 1 from both sides, noticing that I have a denominator of 2. 1 is equal to 2 halves, so I, in effect, subtract 2 halves from both sides, and I get x equals negative 2 plus or minus the square root of 7 over 2. Again, a fairly messy answer, but one we'll come to know and perhaps love, especially if you get it right on the test. So, not a whole lot of fun. And again, the answer is not as bad as the way to get there. A lot of steps that we'll see will become unnecessary. And I mean, some of you may be saying, well, why do you keep saying that? Because I want to impress upon you, as you're watching this, is you say, gee whiz, he does that so easily. Well, of course, he's a math teacher. I'm not sure if I could do that. Well, unless your teacher demands that you do things by completing the square, it's not vital. But I want you to see it. So we've seen a few of these, so we'll see how we generalize to get this formula. Let's use a visual to go back and recap what we've done so we know how to generalize. The very first line, this is the same problem we saw on the chalkboard, 4x squared plus 8x minus 3 equals 0. The first thing we did was to get rid of the number. We added 3 to both sides. Then we divided out the 4. And we divided the 4 by factoring it out perhaps, or dividing each term. Either way, we got x squared plus 2x plus blank, because we're going to fill that blank in, equals 3/4. The 3/4 from 3 divided by 4. The next visual picks up the same problem, x squared plus 2x. We added 1. How do we know to add 1? Because on the second line of this visual, which is highlighted, we see that x plus 1, when we square it, will give us that 2x term in the middle. So we know that we're dealing with x plus 1 squared, and x plus 1 squared will give us a 1 at the end. We add 1 to both sides, and we wind up with x plus 1 squared equals 7/4. The 7/4 were obtained from 1 plus 3/4. That is 4/4 and 3/4. Then we take the square root of both sides. We get x plus 1 equals plus or minus the square root of 7 over 2, 2 being the square root of 4. And finally, we subtract 1 from both sides in the form of 2 halves. The reason we go to 2 halves is to have a common denominator. And of course, therefore, we get our final answer, which is x equals negative 2 plus or minus the square root of 7 over 2. Those are the steps. In our next lesson, we will use these steps in this promise I've made to you to show you an easy way, a universal way, to solve all quadratic equations. And this way will rely upon our ability to understand what completing the square is. Once we've completed the square in general and we have this quadratic formula, you won't have to worry about completing the square until you get to calculus. But the quadratic formula will be quite useful. In fact, you'll find that you'll commit it to memory because it'll enable us to solve all quadratic equations. So until next time, when we have Lesson 16 and the quadratic formula.